Hello everyone, my name is Orang Wahid. The topic of today's webinar is robotics applications with MapleSim and Maple. In this webinar, I'll first start with a quick introduction of MapleSim and basically set the scene for what I'm going to talk about. We are going to go beyond modeling and simulation of robotic system, and by that we will see the analysis of the model that we create in MapleSim or any other task in robotics or multibody dynamics. The topics that we discuss here is going to apply to. Then we will look into the multibody models a little bit more in details and talk about the coordinate selection. And then the rest of this webinar will focus on a case study. And that case study is the Stewart platform. We'll look at the model, the inverse kinematics and inverse dynamics and code generation for that Stewart platform model. And then talk about the conclusions. Okay, so the MapleSim solution. MapleSim is based on our flagship product, Maple. Maple is an analysis environment, is a symbolic computation tool, and has been around for 30 years. It's well known and most powerful symbolic computation capabilities that MapleSim uses as well. And we will see that by using Maple, the equations that you generate from your models can be taken to new heights and be used in various different forms. On top of Maple is MapleSim, which itself is also includes other toolboxes for various different applications. MapleSim is a multi-domain physical modeling environment. It's a schematic-based approach to modeling systems where you have various domains that you basically create models by attaching blocks together. Once the models are created, you can use the connection to Maple for analysis, as we will see in this webinar today. The models that are created in MapleSim can be exported as a C code that the software generates, and that C code can be used to connect to various other platforms like the Space Lab View, Simulink as an S function, or other types of with other types of connectors that we support. So that is the big picture of the software suite that we are going to talk about and utilize today in the applications in robotics. Okay, let's just go to MapleSim at this time and look at a couple of very simple examples that would familiarize us into what the environment is for those who haven't seen MapleSim. So what you see in front of you is the MapleSim user interface. We have on top a canvas or 2D area for dragging and dropping blocks to create the schematics of our model. On the bottom is the 3D view where we have multi-body components. A 3D representation of those components are shown here. On the left, we have various palettes in various domains. We have signal blocks and mathematical blocks for various types of calculations. We have an electrical library, 1D components both in rotational and translational. Multibody, which will be mostly the focus of this webinar, components that you can utilize to create dynamic systems in 3D. And there are other libraries for hydraulic, thermal, magnetic, and also driveline and tire for vehicular applications. So let's just look at how a very simple model is created. As I mentioned, models are created by dragging and dropping components. The first component that dragged in is a fixed frame, basically is a coordinate in a space. and I'm gonna drag a few other components in, and these components we'll just briefly go through them. So we have a revolute joint. As you can see on the right hand side, the parameters associated with the revolute joint. The important one that is the axis of the revolute joint. The connection is made via ports in each component. As you can see, this one is a rigid body frame, and the rigid body frame is basically a coordinate transformation between 2 points, or basically a point in your rigid body. The rigid body includes the mass and inertia. So right now I am defining 2 points in this rigid body, and I am separating them by half a meter. So a quarter meter in negative x and positive x. I can now simulate the model as is, and you can see in the 3D view a representation of this model is shown, and I can do the animation. So this is a very basic model. It's created quickly, but the simulation and what we can do doesn't stop here. We can do various look at various numerical values of components, or keep building up this model and make it more complicated. One way to make this model a bit interesting is to develop it into a slider crank mechanism. For that, I am using one of the examples that MapleSim provides. Under the examples, physical domain, multibody examples, I am going to select a rigid slider crank mechanism. You can see the revolute joints. 3 of them are here, and we have also a prismatic joint, and together they create a slider crank mechanism. The simulation is done the same way as our single pendulum example, and we have a probe for the position of this prismatic or the displacement of that point, and we can see the animation of the resulting motion as the action of gravity. So this is a simple relationship between the components. And as we can see, aside from performing this type of simulation and looking at the plots and looking at the animation, we can do a lot more, which will be a big part of my webinar today. Another example, more sophisticated, I'm going to also choose from the example palette. It's a 5 degree of freedom robot. Let's close this result window. And as you can see on the screen, I'm going to simulate it while we discuss the various components. Again, you can see the various revolute joints that basically create the degrees of freedom of our 5 degrees of freedom robot. We have a base, which is a subsystem. Also includes a degree of freedom, a rotational degree of freedom. And the system, the rigid body links between each pair of revolute joints, as you can see, is connected to electrical motors. Each subsystem, these identical subsystems represent electric motors, and the 1D rotational output of those motors are connected to the revolute joints. So this is what we mean by multi-domain environment. Also, this type of simulation are known as physical domains. So the connections between components represent physical connections. These are not input-output connections. Torque and rotation is related between the revolute joint and the output of each electric motor. And an electric motor is actual electrical component from the electrical library. So you can see that various domains can be put within the same model. Not only we can look at the multi-body side and the effect of various forces and inertias and damping and stiffness, we can also look at how we actuate this with components that represent the electrical side of an actively controlled 5 degree of freedom robot. So this is the modeling environment of MapleSim. What we're going to talk about next is what goes beyond just modeling a system. So let's go back to our presentation and continue. What comes beyond, or what additional to modeling a system and simulating it and looking at the effect of various parameters or taking different measurements as a result of different inputs is the analysis environment. What we call a general purpose symbolic computation environment is something that can be useful in ways that are just not possible or would be very difficult if you want to do hand calculation or just based on numerical calculation. Symbolic computation is a key into a whole host of other types of analysis that we will see a detailed example of later on in this webinar. And a GPSCE, or a general purpose symbolic computation environment, is an environment where we can do symbolic differentiation, for example. And that environment for us is Maple, which is the underlying, which provides the underlying technology for MapleSim modeling and simulation environment. Trigonometric simplification, especially in the field of robotics, we will deal with a lot of trigonometric expressions, and being able to simplify them is quite an advantage, and Maple will provide that. Analytical solving, of course, differential equations that result from any moderately complex system, we will not solve them analytically, but being able to solve subset of the equations that we have, which are always there. There are a linear relationship between variables that can be solved analytically, and being able to do that will enhance the numerical integration or the numerical simulations that we do at the end. And also when we dealing with integrating differential equation, being able to automatically symbolically perform index reduction is very important. Other benefits could be linearization, optimization, and so on and so forth. So for this example that we're going to get into detail of, we have chosen the Stewart platform as a system that's fairly well known, and the equations for it and the way it performs and control are well known to most people that work in the field of robotics. So that's why we selected this example. Before getting to the details of the inverse kinematics of Stewart platform and inverse dynamics, I wanted to talk about the concept of coordinate selection and what MapleSim technology brings to the picture. As we know, selecting state variables or general coordinates will have a very significant impact on the number of equations that we will have to deal with and the complexity of those equations. As an example, if we wanted to model the Stewart platform and we chose absolute coordinates for the entire system, we will have to deal with 78 coordinates, which comes from 12 coordinates per each leg, and also 6 for the platform. The platform has 6 degrees of freedom. So this will end up being 78 coordinates, and that means 78 dynamic equations. But since the Stewart platform has only 6 degrees of freedom, that means we need to also deal with 72 constraint equations. In total, we need to deal with 150 equations. So you can see that in other applications, if the end result is, end goal is to be able to incorporate such a calculation in a controller, for real-time application. The more equations that you have, it means the more computation power that you're going to need. So if we were able to automatically choose a hybrid set of coordinates, which corresponds to both local and absolute coordinates or joint coordinates as well, then we can reduce significantly the number of equations that we need to deal with. And in this case, MapleSim, with the help of its underlying linear graph theory basis for selecting coordinates, will be able to select a hybrid set of coordinates, which end up being only 3 per leg, and 6 for platform, which result in 24 coordinates, and 18 constraint is added to it. And 42 equations is all it needs to represent the system, and eventually needs to deal with when solving or integrating the system. So let's look at the, with that, the first step is better modeling. So just by selecting a better set of coordinates, we will deal with a smaller equations representation of our system. So what we're going to do here is take the Stewart platform system or model and look into inverse kinematic solution of it, and continue that to inverse dynamics, and look into Maple as that general purpose symbolic computation environment to see what we can do in a rather straightforward way, in an intuitive way, be able to manipulate the equations that come from the Stewart platform model, and they are automatically generated by MapleSim. But these are not small equations, these are big complex equations, and the idea of being able to manipulate them as objects is very important, and that's the message that I wanted to convey, is that with such an environment as Maple, the type of analysis that you can do with relative ease is astounding. So let's go back to MapleSim. So first we're gonna look at the Stewart platform model as it's created in MapleSim. You can see the 3D visualization on the bottom and the model on the top. If you look at the model, we have the 6 legs and the platform. Each leg is created by a universal joint, a prismatic joint, and a spherical joint at where the leg is connected to the platform. The important question that we want to answer is, for the inverse kinematic part, is that if we can specify the position of the platform, which becomes the desired position and orientation of the platform, we need to find out what is the extension of each leg, which is the only controlled degree of freedom of a Stewart platform. And that's the inverse kinematic part of this presentation. Then the inverse dynamic part is, now that we have that, let's say we want to implement a controller and we want to do design, we want to know how much force we need to actuate the system with. So the force required for the specific motion, depending on velocities and acceleration that is the desired trajectory of the platform, is calculating those is the inverse dynamic part. So let's start with the simplest way of accomplishing these two tasks, and that will be by tandem, basically using 2 models, one for inverse kinematic calculation and one for driving the system. What we have here is 2 Stewart platform models. The first is driven by the signals, the desired signals that will directly move the platform. And these signals, basically this first model, will act as an inverse kinematic solution. Once we move the platform, we can automatically measure the extension of each leg. And that extension can be measured via a sensor, and that sensor will give us the value we need, and we collect those values, as you can see here, from all of the 6 legs, and we provide them to another Stewart platform model. This one, the difference between this one and the previous one is that instead of moving the platform, we are moving each leg according to the value that we have just calculated. By doing that, we are using the solution of the inverse kinematic, and now that we are moving the each leg or extending each leg according to the value that we have just calculated, we can utilize the dynamic equations and find out how much force are needed to basically adhere to that constraint that we are applying. And that force will be the solution of our inverse dynamic. So with this scheme, we have solved the inverse kinematic and inverse dynamic. Of course, we can see that such an approach, although simple and straightforward, could be very costly for more complex models. And the idea here is to be able to use Maple as our general purpose symbolic computation environment to accomplish these tasks without doing what we have done in this first step. So the idea is here to let's just have a look at the next level of the model. So this time I have only one platform, and this platform takes the desired value for the platform. This is the trajectory. I also might add at this point on, we are assuming that the desired trajectory only constitute the XYZ translation, and we are omitting the orientation of platform for simplicity of the resulting equations that we're going to deal with later on. And that's just to make the presentation a bit easier to track. So the idea for this particular model here is that we are providing the position or the desired position of the platform to each leg, and each leg is extended according to the inverse kinematic solution of the Stewart platform, and we end up being with the correct or desired position of the platform itself. So how can we do that is to calculate a block or create a block that incorporates the inverse kinematic equations. And this block is shown here. And we want to go through the steps that gets us to this point, that we will have this block, that the inputs to this block are the position of the platform, and the output of this block is the extension of the leg. Now let's go and see how we can generate the inverse kinematics of the Stewart platform automatically. Each MapleSim model has a place for saving or incorporating the analysis that is done via its connection to Maple software. And that is, as you can see, under attachments. The particular attachment that I'm interested in is the multibody analysis. I'm going to open that. Now we are in Maple, and our model is shown here. Now we're going to access this model through the API commands between Maple and MapleSim. What I'm doing with the first two commands on the screen is making the connection and having Maple generate the equations for the Stewart platform. These equations are the multibody equations of the Stewart platform, and they are ordered in a way that will be useful in the subsequent analysis which we will be talking about. Okay, so this is the result of this analysis. Let me zoom in a little bit for now. The result of the analysis and after the generation of the equation is that the system has 6 degrees of freedom, and it is the model using 24 generalized coordinates, as we have talked about in the coordinate selection, and also 18 algebraic constraints. A list of general coordinates are shown. We have S1 through S6, which are what we want to find for the inverse kinematic part. And then we have the X, Y, Z, which are the position of the platform. We have alpha and beta, which are the two angles for the universal joint that connects each leg to the ground. And we have the angular Euler angles that define the orientation of the platform. As you can see, we also have the reaction forces that are defined by our constraints. So let's have a look at the equations that we have on our hands. We can use the Maple environment to generate the Jacobian matrix of all of the 18 constraints that we have. And as anyone would have guessed, this is a huge set of equations, which for most application is not useful to deal with this huge set of equations directly. But the idea here is that we can still extract valuable information from the structure of the equations. And that is done by looking at the structure of this Jacobian matrix. What we see here is the graphical representation, which each dark block represents the elements that have value. The white ones don't have any values. By looking at this structure of matrix, we can see that each leg is independent. The equation for each leg is independent from the equations for other legs. So we have 1, 2, 3, 4, 5, 6. The only set of values that correspond to all of them, or they share that coordinates, the coupling terms, are the terms that are associated with the position of the platform and the orientation of the platform. Because at this point we are assuming that is known, so these equations do not need to be solved at the same time, which is a huge advantage that we just found out. Of course we knew that, but we just found out that instead of tackling the big problem of solving this constraint equation at the same time, we can only look at one leg at a time. Okay, so what can we do further with this knowledge that we just gained about the system? Well, our intuition tells us that the leg constraints should be identical, and we can check that quickly using Maple. What we do, we take the three constraints for first leg and the 3 constraint for the second leg, and we substitute the same positional values in both of them and calculate the difference, and we will see that the difference is 0. So that will tell us that not only we have to solve each leg constraint equation individually, we only have to solve one. That's also a huge advantage in what we are trying to accomplish here. So let's have a look at the constraint equations of a typical leg that we need to solve for. Still, this is a big set of equations, and we just don't want to blindly try to subject this to numerical methods. We want to have a better understanding of the structure of this set of equation. So we can look at what type of variables are present in each of these equations using Maple. And the result is shown. We can see that the first equation includes alpha, beta, s, and x, y, z. As I mentioned, from this point on, we are setting the orientation parameters, states of the platform to 0 for simplicity. So the only platform positional and that we are going to deal with is x, y, and z. So the first equation has x, y, and z known, alpha, beta, s unknown. The second equation has alpha unknown and the xyz known. And the third equation, alpha beta is unknown and xyz is known. That tells us that we need to solve the second equation for alpha, get the value for that alpha, substitute it in the third equation, solve that for beta, then substitute the two results in the first equation and solve for the s that we were looking for. And we will just do that. So right now in front of us we have the inverse kinematic solution of a Stewart platform. And this was done through looking at the equations and extracting information, manipulating the equations. That's the idea of this part of this presentation, that with a Maple environment, the equations that you automatically extract from a MapleSim model can be used in ways that are just not possible in any other approach to modeling and analysis. What comes next is that we want to incorporate this set of equations automatically back into our model. We want to have a block that represents the inverse kinematics. MapleSim incorporates a language known as Medelica, and we can use that Maple to automatically generate a component based on Medelica from the equations that we have just generated and implement that back into our model. The last line that I just executed creates the components and ask us to replace the current one, which is already existed in MapleSim, to have that set of equation inverse kinematics available. So we have now a block in our definition under components that gets the position of the platform and gives us the S, alpha and beta of each leg. So we have an inverse kinematic block. Okay. Now we want to do better than that. Right now we have the inverse kinematic blocks, which we use to actuate each leg, and then use a sensor, a force sensor, to measure how much force is needed to move each leg according to the inverse kinematic solution, which gives us the forces or inverse dynamic solution of the Stewart platform. We want to know if we can do this calculation in a straightforward way without going through the multibody analysis. So let's continue on what we were doing and basically continue on inverse dynamic calculation. So for that, we will first need to define the basic relationship. As I mentioned, we will set the zeta, eta, and xi to 0. Also the first and second derivatives to 0 for this particular example. And then look at the constraint equations and see which one includes what variables. And the same thing that we did with the constraint equations, we can do here. And you can see that the dynamic equations that we have for the entire Stewart platform, this is the structure. And this structure basically tells us that in which variable exists in what equation, and gives us a plan of attack to find the solution. We can see that from equations 10 to 21, these equations, here we have alpha and beta and S, alpha and beta and 1 to 6, meaning leg 1 to 6. So these are known. We have the inverse kinematic solution. So we can use these equations to quickly find Fy1 and Fz1, and these can be quickly calculated. Once those are known, we can use the remaining 6 equations to find Fx's, which is the forces exerted by the actuator in a prismatic joint. So let's do that. We use Maple to quickly solve, and we only display one in a symbolic form. And then we can do the same thing for the rest. But these are big equations. So we will do and these are linear in terms of our unknowns. So we can do convert them to ax equals b. And along the steps that we are taking to create ax equals b, we can check our calculations so that we, for example, in these two set of calculations, we are checking to see we haven't missed any terms. These are important steps that you need to take while you're doing symbolic manipulation or any type of manipulation on a big set of equations. You need to at each time make sure that the results that you're getting is what you expected it to be. So these quick checks to see left-hand side and right-hand side are still create the same equations that we start with, or the ax equals b after we created the matrices is important. Once we have done that, we can have the linear solver of Maple to just solve those huge set of equations. And as you can see on the screen, if I zoom in, the result is too big to be displayed on screen. We can just look at one of them for F1, for example, and these values shown in a closed form, that if we have, for example, S1, assume known, first and second derivative of it, alpha and beta, then we can calculate the force needed. So that's the inverse dynamic solution. And we can incorporate back into a block that calculates the system. It's important that we can perform a check to see that during all of these symbolic manipulation, our final results, what are they dependent on? Because there might have been instances that we have missed something, so we want to do a quick check. And as a result of this command here, we find out that our results, the forces, are only dependent on alpha, beta, s, and velocities, which is what we would have expected to see. Now that we have this huge set of equations that will be our inverse dynamics, we can use Maple to create a C code that represent that. For the inverse kinematic, we incorporated a Modelica approach to bring those equations back into MapleSim and incorporate it into our simulation. For the inverse dynamic equation, we are choosing a different approach, and that is to bring back the equations in the form of a C code block. So we need to define the inputs. So the inputs to the force calculator block is the displacement of the prismatic joints and its first and second derivatives, and also alpha and beta angles for the universal joints and their first and second derivatives. So that will be the inputs of our S function, the C code that represent that function, that represent the inverse dynamics of the Stewart platform. And we do some bookkeeping of variables. We have, for this particular block, 63 inputs and 6 outputs, and we assign a vector of variables so that will be used in the automatic code generator. And that code generator, we can calculate how much calculation cost is associated with such a calculation without doing any optimization. I'm going to zoom in again. So that calculation that we want to implement is shown on the screen right now. How many additions, multiplications, subscripts, functions, division, and assignment is involved. and you can see it's 100,000 addition is required, 300,000 multiplication is involved. But we can use Maple technology to optimize this huge set of calculations symbolically. By that, we mean what is meant is when you have a big set of equations, there are a lot of trivial calculations that if you are not doing the optimization symbolically, you need to pay the price for it each step. There are repeated expressions that you will calculate over and over again. If you can in some way detect it and isolate it, then you will only calculate it once. There are different levels to this optimization, and this is the result of that optimization. You can see that we have 24 function calls, and the addition is gone down to only 328 additions and 500 multiplication. So that's a huge reduction in the computation effort associated with the inverse dynamic calculation of the Stewart platform. And the idea is to show that this type of calculation can be done in other robotic applications that would end up being incorporated into a controller, for example, or a real-time application. And we can create that procedure based on C, and then these are like 100 first characters, and then incorporate that C code back to our MapleSim model. What I'm going to do is basically show you the resulting MapleSim model that incorporates the inverse kinematic block and also the inverse dynamic C block. The inverse kinematic was a Modelica coded automatically, and the inverse dynamic is a C code. So this time we don't have any multibody components. And we'll still have 3 inputs coming in, which are the position of the platform. And what we do calculate is the 6 forces for the 6 legs. So the actuation forces required for each leg for the particular trajectory that we decide on for the platform is automatically created within this block. Let's see what's inside it. Inside this block, we have our C code that we just generate, which incorporates or includes the inverse dynamic equations. And this block needs, as we have seen in the Maple worksheet, we can just revisit it again, that the inputs required for this C code involved the position and the first and second derivative of it, and all the angles and the first and second derivative of that as well, and also the velocities of the input signals that are desired trajectory of the platform. So if we look at what is done here, is the input, the desired trajectory is taken, and here fed into an inverse kinematic block, the one that we created previously. And since we are in a symbolic world, we can avoid introducing numerical errors by doing a numerical differentiation of our signal. We can do that symbolically. So we have symbolic differentiation blocks, 2 of them for the first and second derivative, and these blocks are used to calculate the signal first and its second derivative for all of that, and then all of that is combined and given to the C block, and the result of that will be the forces for the inverse for the Stewart platform. So what we would see, and there's a slide that I will show you after I'm gone back to the presentation, that we will get a huge boost in the time for the calculation required for the inverse dynamic. The first option was traditional, or the straightforward way of having 2 Stewart platform, one for inverse dynamic and one for inverse kinematic. The second option was to solve the inverse kinematic and implement that. And the third that we see on the screen is just to calculate everything into one big function and just implement that. But before leaving this example, I want to show you what else we can do with environments such as Maple, and that would be to do parallel computing. Not only we can speed up the calculation greatly, we can also perform parallel computing in a rather straightforward way using Maple. What I'm doing right now is getting the entire procedure that solves the model, the inverse dynamic model of a Stewart platform, and basically going through various trajectories. I'm changing the amplitude in 100 divisions, changing the frequency into 100 division, and calculating the maximum force the actuator need to provide for all of these cases, 10,000 cases of simulation. I'm going to perform that repeated calculation. For each simulation corresponds to 7 seconds of simulation time, and 10,000 of those simulations are being performed. As you can see, I am utilizing almost all of my CPUs, and the results will be shown within a few seconds. And so the code in Maple technology for parallel computing is straightforward, and the task-based code approach is implemented here, and you can see the results. 10,000 simulations, each 7 seconds long. The entire simulation took about 27 seconds, which is pretty fast. And the results of the maximum force of the actuator versus amplitude and frequency is shown in the 3D plot. Okay, so let's go back to the presentation and reach the conclusion of this webinar. To test the performance of the models that we have seen, the 3 Stewart platform with inverse dynamic solution that we have you have seen, we chose to create a C code for the entire model and export that as a Simulink S function, and use 100 seconds of simulation time. Chose an Euler solver with a time step of 1e-3, and then compare the results to see how much more efficient the calculations become as we move on from the traditional way, the first model, to inverse kinematic solve, to inverse kinematic and inverse dynamic solve. This is the result that we have gotten. On the hardware that we have used, the actual model, the first model that has 2 Stewart platform running, was ran 4 times faster than real time, which is significant as is. And some of that goes back to the way equations were generated to begin with. We were using a linear graph theory, so we were dealing with a smaller set of equations, which is a huge boost without doing the inverse kinematic and inverse dynamic the way we did. Once we remove the one model and perform the inverse kinematic via that Medelica component that we incorporated in our model, we become 2 times faster, or in total 8 times faster than real time. And once we solve everything, the inverse kinematic and inverse dynamic, the final result was staggering 66 times faster than real time. So this basically presents you with the option of doing a simulation in an environment that is multi-domain, physical environment, which makes it intuitive to create complex models within various domains. Being able to use the general purpose symbolic computation environment to do analysis on the set of equations that are automatically generated, being able to automatically create components based on the equations that we have, and also being able to code generate the entire or part of the model and incorporate that back into our model or use that for real-time application. Just to a few conclusions for this webinar. MapleSim is an ideal tool for modeling and simulation of dynamical multi-body systems. MapleSim multi-body technology, together with the powerful symbolic computation capabilities of Maple, enable the users to perform modeling and analysis tasks that are not possible any other way. Symbolic technology is a proven engineering technology that significantly improves performance of real-time simulation for complex systems.